unit, which is radiation. So let's get to it. So radiation basically travels as electromagnetic radiation, which is the transmission of energy through space without physical connection through varying electric and magnetic field. An example of this is light. Visible light is just one part of the electromagnetic spectrum, and I'll show you what all of that looks like in a little bit. So to understand this, we need to understand a little bit about waves. So just some basic information on waves. The wavelength is basically the length of one wave, which needs to include a crest, which is the top, and the trough, which is the bottom. So you can measure wavelength really from any point on a wave to the same point on the next wave. So easiest way to normally do it is from crest to crest or trough to trough. But really any point on one wave to the same point on the next wave is fine. And then amplitude is the measure of from the undisturbed state, or sometimes referred to as the rest position, up to the top or bottom, to the crest or the trough. So the amplitude is basically a measure of how strong or how powerful the wave is. One example would be a wave in water. The water just simply moves up and down, but the energy goes from wherever whatever made the wave started to wherever the wave stops. So the medium just goes up and down, but the energy goes from one place to another. It's important to understand that the medium doesn't really move all that much. Frequency is the number of wave crests that pass a given point per second. Period is the time between crests. So, and the mathematical relationship between those is period equals 1 over the frequency. And another way to say that is that they are reciprocals. So period and frequency are linked. So if you have a frequency of 5, that means then that would be 5 hertz. Hertz is the unit that we use to measure that. So if you have a frequency of 5 hertz, then you have 5 waves per second, which means that each one of those waves has 1/5 of a second to travel. So you can see how they are inverse in that way. Wavelength, like I said, is the distance between successive crests, and velocity or wave speed is the speed at which the crests move. And the relationship between all of this is the speed or velocity equals wavelength times the frequency, or wavelength divided by period, since they are reciprocals. So like I said before, the visible part of the spectrum is just one part, and it's actually kind of blown up here. It's actually smaller than this, but the electromagnetic spectrum includes radio waves, infrared waves, visible, UV, X-ray, and gamma rays. The higher you go to the right, the more energy, higher frequency, but shorter wavelength. The more you go to the left, lower energy, lower frequency, longer wavelength. So waves and what? Water waves, sound waves, and so on need a medium, which means they need something to travel through. One of the two major differences between electromagnetic waves and what we call mechanical waves, which is every other kind of wave. So you basically, the two large categories are electromagnetic waves and then mechanical waves. Water waves would be a mechanical wave. The differences here are that electromagnetic waves don't need a medium. This is incredibly important because if they did, then we wouldn't be able to get light and information through space, because space is, relatively speaking, empty. It's not enough of a medium to carry the particles, or I should say the energy. The other difference between electromagnetic waves and mechanical waves is that EM waves are three-dimensional. They have an X, a Y, and a Z axis. So very hard to conceptualize. So here's the drawing. Most mechanical waves just have an X and a Y axis. Here you can see you have two different vibrations. You have an electric field vibration and a magnetic field vibration, and those two oscillate. Speed of electromagnetic waves, and this is the speed of all electromagnetic waves, is the speed of light, which is roughly 3.0 times 10 to the 8th meters per second. Speed is large, but it's still finite, which means it still has a limit. It can take light millions or even billions of years to traverse astronomical distances. Then we're not going to cover some of these things quite so much, but diffraction is basically what happens if you poke a hole in something and then the light travels through the hole. You end up getting kind of some weird patterns out of that. We don't need to get into that too much. Here is just another example. This actually shows you how big the electromagnetic spectrum is and how much light is a small part of that. And then this down here, this is the atmosphere and what can get through the atmosphere. And you can see the transparent part of it is down here and then here, which means that the visible light can get in and the radio can get in. The good thing here is the X-rays, the gamma rays, UV rays, most of them can't get through. So that's one of the things that protects us. The Kelvin temperature scale. Kelvin temperature scale is basically the same as the Celsius scale, only you back it up to the point where thermal motion ceases. So if you think about what energy is thermal motion. It's the motion of particles. So I should say that's how we measure temperature. So if you really want to get particular about it, you really should start the temperature scale at 0, which would mean 0 thermal motion. So that's what the Kelvin scale does. So notice it's the exact same as the Celsius scale. So 0 Kelvin is equal to negative 273.15 degrees Celsius. And then you just adjust everything from there. The Doppler effect. Doppler effect is important. Basically, if you're moving towards a source of radiation, the wavelengths get shorter. If you're moving away, they seem longer. So with light, what happens is that if you're moving towards a source of waves, the light will appear to be bluer. Whereas if you move away from a source of light, then they will appear redder. This happens with sound as well, and you guys have all heard it before. If you're moving towards a source of sound waves, it will actually go higher in pitch, or if that source is getting closer to you, like think of a train whistle or a fire engine siren. Once it goes away from you, the pitch goes down. So this is just the visible light part. So this is what's called a red shift if you're going away, or the blue shift if you're going towards. Then this is really, really important. Actually, we're going to talk a little bit about it later. And this is just more stuff on the Doppler effect, but you just need to, this is a good visual, just showing you what happens to the waves. So you can see the waves get spread out over here. So spread out, lower frequency, turns redder. Squish those waves together, higher frequency equals bluer. So higher frequency light equals a bluer light, lower frequency light equals a redder light. And we use this in a bunch of different ways. One way is through using a radar gun.